So hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have the Travis Addair from the Predibase to give us this talk about the efficient LLM inference. And Travis is currently co-founder and the CTO of the Predibase, the platform for fine-tuning and serving task-specific LLMs. And he's the author and the lead maintainer of the LoRAX, the LLM inference system for serving thousands of fine-tuned LLMs on a single device. Within the Linux foundations, he is the lead maintainer of the Horovod, the open source distributed deep learning framework, and is also a co-maintainer of the Ludwig, the open source declarative deep learning framework. So in the past, he had led the Uber's deep learning infrastructure team as part of the Michelangelo machine learning platform. So let's welcome Travis to give us this talk. So Travis, it's your turn.
All right, thank you for that introduction. So hi everyone, I'm Travis, and today I want to talk about this open source project that we released a few months ago. It was November of last year, called LoRAX, which is a project that's all about LLM inference, but specifically figuring out ways that we can make it very scalable to serve fine-tuned and task-specific LLMs. And I'll also be spending a bit of time talking about this, I guess, philosophical direction of parameter-efficient inference more generally, and some of the kind of speculative or future-looking opportunities that I think it presents when compared with more traditional ways of thinking about LLM inference. So as a bit of background, one of our favorite quotes slash pseudo mottos at our company is that general intelligence is great, but we don't need a point of sale system to recite French poetry. And what we mean by that is if you think about the current landscape of LLMs and in particular, deep learning in general and then LLMs in particular, what you see today is that there's a lot of excitement around these very general purpose models that can do lots of things. ChatGPT obviously being the really famous example of that. And I think that that's very great for certain applications that are very open-ended. But once you start figuring out what your use cases are for an LLM and what kinds of query patterns you want to be throwing at it in production, you very quickly realize that you don't actually need a backend system that can do, innumerable number of different tasks. Like you really want something that's very specialized and fit for purpose, because that's ultimately going to be cheaper, faster, lower cost of ownership, et cetera, than trying to use, a sledgehammer to do every single task that you might have. And so when we think about this kind of progression that a lot of organizations go through when they are exploring generative AI, we see this pattern play out a lot, where someone will use something like GPT-4 as a starting point to get an experiment off the ground because, it's all exposed through an API. They don't have to do any fine tuning or anything like that in order to get value. They just have to do some prompt engineering, maybe some retrieval augmented generation. But as they start getting something working, they start to run into these roadblocks. For example, there's a lack of model ownership, which means that GPT-4 can push an update to their model at any time that completely breaks your production system. You don't really have any control over that. You need to give access to your data in some way, whether that's on the fine-tuning side or even just on the I'm sending requests to them and they're able to do whatever they want with that and with the response. Particularly if you're doing RAG, you're probably putting sensitive data in there. And it's also too slow and expensive and overkill for a lot of applications. So a lot of people might have a simple use case that boils down to, predicting the next few tokens, like in a Gmail type ahead type scenario, where they want something to be responded in the order of tens of milliseconds, whereas GPT-4 can't really guarantee that. So there are lots of cases where latency, throughput, predictably the service level agreement that you get from your provider, your model providers, is very critical. So the alternative that we have in mind, that we see companies that we work with exploring, is this idea that instead of having one big monolithic model, I will train lots of different specialized models depending on my specific tasks and use cases. So I might have a Mistral 7 billion fine-tuned to do customer support, triage, or prioritization. I might use a Llama 2 70 billion as a chatbot. I might use a smaller model like Gemma 2 billion to do customer sentiment analysis. And the benefits of this is that ultimately what you're able to do is you're able to have complete ownership over the models. You don't have to share your data if you're training it all in your VPC, et cetera. Smaller and faster footprint, and you're able to more precisely control the output of the model by, manipulating logits and things like that. And what we find is that this ultimately leads to better performance in addition to the smaller footprint. So this idea of fine-tuning these specific models, here's an example where we were looking at a task of JSON generation. GPT-4 zero shot was giving 66% accuracy on this task, but a 7 billion parameter model was able to get 40% better accuracy at a 250x smaller footprint, right? With just very fine, very, very modest amounts of fine tuning on top of that. And we see this pattern play out a lot, actually. So we did recently a set of benchmarks across a variety of different tasks, looking at Mistral 7 billion fine tuning for versus GPT-4, and found that in all but a couple of cases, and in those cases it was more open-ended ones like code generation, doing very simple LoRA fine tuning with a small rank parameter gave pretty significant performance improvements over GPT-4 out of the box. And this is something that we see a lot of organizations realizing as well. So this idea that you might want to be fine-tuning lots of different task-specific models is something that we think is a direction that lots of different organizations are going to be exploring in the future. And there are lots of different use cases for why someone would want to be exploring this. For us, Predibase, we started thinking about this problem because we're an AI platform that has lots of different customers. So we certainly think about the problem of if each of our customers is fine-tuning some number of models, how are we going to support that? What's our infrastructure going to look like? But other organizations might have other reasons for wanting to do multiple fine-tuned models. You might have segmented models where it's the same task, but a different user or a different product or a different region. This was one we saw at Uber quite frequently, where almost all of our models were customized or trained specifically for a particular region, just because the distribution of data ended up being quite different. You might have lots of different tasks that you want to do because you have an agent-based system or a workflow that you want to run, say customer support, where you have something like a triage step or an intent classification step. You have a remediation that you need to compute. You have a response that you need to generate, which would be like an email. All of those could be separate models. You also have things like speeding up task-specific workloads, so being able to reduce latency through techniques like speculative decoding, which also require fine-tuning for some of the best techniques. And personalization, so being able to steer models towards responding in certain ways, like traditionally this would be something like direct preference optimization, but you can also do it with more parameter efficient techniques like control vectors are a recent one that's becoming more popular that I'll talk about. So there are lots of different things that you can do with building fine-tuned models, and lots of reasons why you might want to do more than just one of them, right? Instead of fine-tuning like one big model, you might want to do lots and lots of different task-specific models. So assuming that an organization is on board with the idea of fine-tuning multiple different task-specific models, then the question that we start to think about is how much is this going to cost? And here's kind of a rough breakdown of pricing per hour on AWS on demand without any incentives or anything like that. Typically, the A10G is about the entry-level GPU that you'd want to use for serving an LLM at about the 7 billion parameter level. And that one runs about $1.21 an hour and gives you about 24 gigabytes of VRAM. And so if you think about extrapolating that out to how much it's going to cost per month to stand up such a serving stack when you have 1, 2, 4, etc. fine-tuned models, you realize very quickly that once you start getting past, the very small number of fine-tuned models and start getting to the tens, you're starting to look at tens of thousands of dollars per month in AWS bills to serve all these models if you're serving every single model on a single dedicated GPU instance. And so this leads us back to this idea of fine-tuning and the way that we think about creating these fine-tuned models in the first place. So conventional fine-tuning, just as a quick refresher, we have a forward pass through the model. We have some weights at every layer that we'll call W. And then we have a backward pass where we actually update the model parameters and compute some gradients and apply those gradients for the update step. And the gradients and the weights that get updated are the entire weights of the entire model in most cases. And so the checkpoints that we generate are quite large, and the cost to load in the model and to memory the fine-tuned model is the same cost as the base model. But there is, of course, another way that I think most people are pretty accustomed to now, which is parameter-efficient fine-tuning, and specifically this is low-rank adaptation, or LoRA, where in addition to having the original parameters, you introduce a couple of additional parameters at certain key layers. In this case, you have this A tensor and this B tensor, and these form a kind of low-rank decomposition of the shape of W, so that the size of these two parameters added together is significantly smaller than the size of the original parameters W. And then when you do the backward step to update the parameters, you only update those low-rank parameters that you introduce. You leave the original parameters untouched. And so this has a couple of benefits. One is that it reduces the amount of memory that you need to fine-tune the model, because it reduces the, in particular, amount of state that needs to be tracked in the optimizer. But it also reduces the checkpoint size of the fine-tuned model on disk, which then also means that when loading this model at inference time, the amount of parameters that you need to load in addition to the base model is very small, usually on the order of about 0.1% to 1% of the original model parameters. And so if we think about how this translates to inference, we can look at something like this as a bit of an example of how such a base model plus fine-tuned adapter would look as a serving deployment. So if you're using Kubernetes, you might have something like a pod here. You have a user sending the request to a request queue. In orange, you have the base model parameters, and in blue, you have these adapter weights. And if you're going to be serving multiple of these, again, the kind of straightforward way to do it would be, let's create a Kubernetes pod, which equals a GPU per fine-tuned model. But you see very quickly that, the vast majority of these parameters are in fact shared between these different deployments. And so the natural question then is, well, could we just have a deployment that has all these orange parameters here and then loads multiple of these fine-tuned adapters at the same time, so that we don't have to constantly be spinning up a new deployment as we are here? And that's ultimately finally now getting to what I really mean by parameter efficient inference, is this idea of these parameter efficient LLM deployments, where we have a single deployment, so a single Kubernetes pod, for example, that has multiple different users requesting different fine-tuned models, serving the same base parameters once, and then serving each of these fine-tuned adapters together on this single deployment, right? And so this is ultimately what LoRAX is doing. What LoRAX is all about is it's a framework that lets us serve hundreds, potentially thousands of these fine-tuned LLMs on a single GPU, so at the cost of one deployment. And this next section of the talk, I'll spend a bit of time talking about what are some of the optimizations that LoRAX implements in order to make this possible and make this efficient, and then talk a little bit about some of the benchmarking numbers on how it works in practice. But before that, let me just briefly show from a user perspective, like how to get started with something like LoRAX. So this is how you would launch a LoRAX server. You would just essentially run our pre-built Docker image is the recommended path to doing so. you would define some kind of volume from your host that maps to a volume in your container so that you can cache weights that are downloaded so you don't have to re-download them every time you run the Docker image. In this case, we're just going to launch a Mistral 7 billion instruct base model and run it within the container. And then once it's up, it's pretty easy to get started with prompting it. So we do have a client that we ship that you can use to send your requests. And if you want to send a request to a particular fine-tuned adapter on Hugging Face, all you need to do is provide this additional parameter here called adapter ID. So here we're using this adapter ID that was fine-tuned on the GSM8K grade school math data set. And so in theory, if everything goes according to plan, when you prompt the base model, it should give you something not quite what you're looking for as an answer to this question. But then when you go ahead and provide this adapter, because this adapter was fine-tuned specifically on a data set that looked like this, it should give you the correct answer to this question. And the nice thing here is that this adapter is going to be downloaded from Hugging Face, loaded into GPU memory, all at runtime, so you don't have to think about how to structure the adapter folder or anything like that in order to expose it to the server. We'd also implement an OpenAI compatible API here. Instead of having the model parameter specify the actual base model, you just put a LoRa adapter here, and it will dynamically load in that adapter. And then it will apply the chat template for the adapter when rendering out the system, user, etc. messages that you send in your request. So all of that also gets handled under the hood by LoRAX. So that's a bit about how LoRAX gets used. And now to get into some of the meat of the presentation, I'll go ahead and talk about what we're doing kind of under the hood that makes this possible and makes this scalable. So in particular, there are three optimizations that I'll be talking about here. The first is how the dynamic adapter loading system actually works. The second is the scheduler that we implement to enable scaling to more adapters than fit within memory. And the third, and probably the most important one, potentially, is the heterogeneous continuous batching process that enables us to handle multiple requests for different adapters concurrently in the same forward passes without having to do any swapping or time sharing or anything like that. All right, so for dynamic adapter loading, just revisiting this image again quickly, the basic idea is that you have different requests coming in for different LoRa's. And then let's say you have a third request here come in for a new third LoRa. What LoRAX will do is it will load in that adapter dynamically in the background. And this will be done in a non-blocking way. So all these requests coming in for the red and the blue adapters, those can continue to be processed as usual while the download is happening in the background. And then once this LoRa, this green LoRa has finished downloading, it'll then be eligible to accept requests as well. But until then, it'll just kind of sit there in the background waiting on the queue. Kind of a sequence diagram here that shows how this process works in practice. So a user sends a request from their client to our backend system. There's a router that will then send off two different requests. The first will be a request to this adapter manager entity whose job it is to say, hey, I don't have this adapter. Let me go download it. And in parallel, we'll send a request to the batcher saying, hey, there's a new request coming in. It has a particular adapter that it wants to use. Let me go ahead and activate that adapter so that I can begin sending requests to the model for that adapter. Once the download process completes, a notification gets sent back to the adapter manager saying, hey, this adapter is now in the downloaded status. And I also have a request to activate it. So let me go and now load that adapter onto GPU memory. Once the loading is complete, we get another callback back to the batcher saying, hey, the adapter is now downloaded. It's on the GPU. You can go ahead and put in the batch and begin sending requests to the model for inference. And at this point, we'll go ahead and run the normal prefill and decode steps. So prefill will be generating the first token, and then the decode step will be the iterative step thereafter, where we generate the subsequent tokens. And then once the generation completes, we send the response back to the router and then send the response finally back to the client, such that it now has the final response. As I mentioned, there's also a scheduling component that lives within the batcher part of the stack that handles which adapters should be active at any particular time. By default, we try to pack in, we reserve 10% of the GPU memory for loading adapters into memory, into GPU memory. And if that threshold gets exceeded, then we have to start doing a bit of a offloading strategy in order to make sure that we can service all of the requests coming in for all the different adapters, right? So the scheduler's job is to say, okay, who among these adapters has been active, so meaning on GPU, for the longest amount of time? And then once certain adapters have been active for longer than a certain period of time, some threshold time, which we default to 2 seconds, we'll go ahead and offload it and then swap in one of the adapters that's sitting on host memory onto the GPU so it can also continue to process requests. And so this hyperparameter of this cycle time, this time between that we allow it to be active before we swap it, is an important one in the case of very, very large numbers of adapters, because that ultimately determines whether you're prioritizing throughput, so being able to batch requests for the same adapter all the way through to the end of generation, or if you're prioritizing kind of worst case latency, so how long it takes for a particular adapter to begin accepting requests, because you can imagine if the same adapters are sitting active on the GPU processing requests for a long time, that creates a bit of a starvation problem where the pending adapters are just sitting there, they're not getting serviced, and users are starting to wonder why it's taking so long. So that's the scheduler's job ultimately is to try to balance between these different concerns and ultimately produce a good balance between latency and throughput. And then finally, there's heterogeneous continuous batching. And this is the one that certainly had the most interest from the academic community. There's been a number of papers written on this subject. The first that I was aware of was one called Punica that came from University of Washington, which introduced this idea of the segmented gathered matrix vector multiplication, which I'll talk about. But one that might be even more famous is a paper called S-LoRA that came out of UC Berkeley, where they talked about a similar extension to that idea that supported discontiguous LoRa memory using a KV cachings like the storage mechanism, similar to how the page detention algorithm works. But regardless, there's been a lot of interest in this area because I think there's been a broad realization that if you don't solve this problem of batching together requests for different adapters at the same time, then essentially you lose all the benefits of continuous batching, which is probably the most important optimization in LLM inference today. So definitely an important one to solve. And I think a good place to start here is talking about how you would kind of naively think about solving this problem. So just to make sure we're all on the same page about what exactly the context is, let's say you have a batch of 5 different requests here, and each color here represents a different request or row in the batch for different adapters. So you have an adapter, a blue adapter, 2 requests for this red adapter, another request for a blue adapter, and then a request for this black adapter. And then you want to start by multiplying it by the base parameters W's, kind of typical LoRa process. And then you want to accumulate the contribution for each of the LoRa adapters at each of the rows in this batch. So how would you do that? Well, first row here is for blue. So we're going to then do this index lookup saying, okay, first row needs LoRa index 1. Let me go and grab that. The LoRa A matrix goes here. Let me grab the LoRa B matrix. It goes here. And then we do the multiplication, input, matrix multiplied by A, matrix multiplied by B, add that back to the original output for this particular row. And then we repeat this for however large the batch is in terms of how many rows it has. So this works, but you very quickly realize that it does not scale particularly well with the size of the batch because you're having to do many different forward passes for each of these operations for each of the rows. And there's also some redundancy, right? Because let's say, all of these what if all of these rows were for the same adapter? You'd ideally just want to vectorize this, do like a single instruction, multiple data thing one time, and then be done with it. You wouldn't want to have to, go row by row. That loses a lot of the benefits of systems like GPUs in the first place, right? All right. So is there a better way? Yes, there are certainly better ways that we can do this. One, for example, would be, well, what if we just, instead of going row by row for the computation, what if we gathered together all of the LoRAs based on the index into a big three-dimensional tensor that has shape, batch size dimension by LoRa rank, by the hidden dimension, and then put that here, and then did that for the B as well, and then did the matrix multiplication all at once, where you essentially say row, all the rows in the batch times the LoRa A combined matrix, or tensor rather, and the LoRa B combined tensor, and then go ahead and just apply that all at once. And so the only additional overhead at that point is the overhead of constructing this gathered tensor in the first place. And that works a lot better in practice, but it's still not optimal. In particular, you are still having to create this gathered tensor at every step, which is expensive and a bit redundant. And also it doesn't support, things like dynamic shapes or situations where some of the rows want to use an adapter and some don't. And so that finally brings us to some of these more novel research ideas, like the SGMV operation that Punica put forth, which is very similar to the gathered implementation that I showed. But the big difference is that instead of actually performing a gather step where we bring all of the LoRAs together into a single tensor, instead they just maintain a vector of pointers to different LoRAs. And then at the CUDA layer, they actually will do loading of individual tiles from those LoRAs as part of the kind of normal processing of the within the CUDA kernel to load in tiles from those tensors through the indirection that comes from the pointer, and then apply the matrix multiplication kind of one tile at a time that way. So there's no need to bring all the data together at once before then running the computation. We just do this in a streaming and parallelized way to begin with. And this ends up being much more performant in practice than either of the other two approaches that I showed before. And just to make this really concrete, this is numbers from LoRAX itself. Actually, we do support the loop-based implementation as a fallback mechanism in cases where the SGMV kernel can't apply because of shape issues or things like that, dimensionality issues with the model. And what we see in practice is that the throughput that you get from the looped implementation starts off pretty good when you have a low number of adapters, but very quickly degenerates to a point where once you have 128 adapters or so, you're down to about a tenth of where you started from. So definitely there's some significant degradation. But the SGMV kernel does a really good job of maintaining very high throughput with very little, if any, noticeable degradation, even up to 128 adapters. And this is 128 adapters that are all coming at the same time, being batched together in the same request. So a pretty substantial level of load that you're unlikely to see very commonly in production outside of very heavy scenarios. Very similar story for latency. The loop-based implementation scales essentially linearly as we increase more adapters, whereas the SGMV implementation maintains essentially constant latency, even up to 120 adapters. So very good scaling properties across the board. And ultimately, all of this translates to lower cost of ownership, which is, I think, the most important thing that we personally think about from our perspective. And this is a breakdown comparing LoRaX with multiple different fine-tuned models versus dedicated deployments and the costs that you would incur for different adapters, and also comparing against OpenAI, which supports a serverless fine-tuning experience at a constant cost, but has a very, very high baseline cost. So the important thing to note here is that OpenAI is very expensive to start with, but once you kind of go somewhere between 16 and 32 fine-tuned adapters, the cost of OpenAI is actually lower than the cost of dedicated deployments. But LoRaX is lower than both of them in general. So the kind of baseline cost of LoRaX is quite low, but crucially, it's also quite low even at the high scale, and does not essentially creep up, unlike the dedicated deployment. So definitely a big motivation if cost is a primary concern. A few other things to call out are some other optimizations that we have built into LoRaX. So multi-GPU/tensor parallelism, we do support it. It's based on an algorithm that was proposed by the authors of the LoRA paper. So this is a diagram that they had in their paper. We implemented this same strategy. It is quite communication intensive, so we don't recommend doing tensor parallelism, so multi-GPU, unless you have NVLink set up between your GPUs. We notice that's quite slow with PCIe. But when you do have NVLink, this works quite well and allows you to get a lot of benefits out of those multiple GPUs. So credit to the authors here for proposing that algorithm. We also implement coup de graph compilation. We found that this in particular works very nicely for smaller models. So models like Phi-2 tends to provide some significant performance improvements. Kind of GPT-2 medium here, you can see there's a bit of an over 2x increase in tokens per second. So definitely something that is worth exploring as well. And then another feature that we've added recently is structured generation. So the ability to enforce that the model outputs things in a particular format, usually JSON format. So here you might have, a model that you want to generate some character for a role-playing game. You have some armor, some strength, a name, etc. And you prompt it saying, hey, generate a character for my game. And then you just tell it response format needs to be in JSON and needs to adhere to the schema. And then as you can see, when you load it in, you can load it using the JSON load string function, and it'll work without any errors because the model is guaranteed to produce only valid JSON at that point. And this sort of structured generation is not just nice for enforcing schema format, it's also nice for improving model performance. And what we found empirically is that this combination of structured generation to a schema with fine-tuning actually works better together, where the schema enforcement helps ensure that we avoid any edge cases where the model might miss a comma or miss a closing bracket or something like that. But the fine-tuning does a good job of ensuring that the model and the structured generation process end up populating the right content in the right field. So in practice, what we found is that fine-tuning also benefits these sorts of JSON extraction tasks as well. So that's a bit about LoRaX and some of its features and optimizations. Last thing I wanted to touch on in this presentation before kind of opening it up to questions is a bit about other parameter efficient techniques beyond LoRa that I think are very exciting. In particular, classification heads, embedding, fine-tuned speculative decoding, techniques like Medusa and speculative streaming, control vectors, and model merging. So I'll talk about those each a little bit. Classification, I think, is a really natural place to start because it's a very common production use case in the wild. And I think a lot of people use LLMs for classification tasks, but they actually use them for classification while still doing the kind of traditional token by token generation. But if you're really just trying to classify like one of 3 different labels, what you can do is find some way of pooling the final hidden state outputs that come out of the model. In this case, they just select the first one, but you could also aggregate them in some way, like averaging them out. And then pass that through a classification head, which would be a simple multi-layer perceptron or just a simple projection layer that goes from this dimension to the dimension of the output. So maybe you have like classifying something as red, green, blue, then you would just have 3 different output probabilities at the end, and then you would just figure out which one is most likely. And the nice thing here is that this additional parameter here, that this projection that does the classification, is the only new parameter that you need to introduce to the model for this, but can give you a pretty significant performance improvement. So very useful parameter efficient technique to apply in production. Similar concept for embeddings. So you can have a model that generates sentence embeddings, but there's also this interesting approach of doing domain-specific adaptation for improving retrieval of a specific corpus of data. And in those cases, you can train this domain-specific adapter, which is usually just another projection, right, from the hidden state of the original model to some additional embedding dimension, and then just essentially applying that MLP to the original output of the model and using that for improving your embedding generation for tasks like retrieval augmented generation. Speculative decoding is one that I'm personally very excited about, and we're actually adding this to LoRAX this week. So in the case of Medusa, which is one of the most popular ones, what you do is instead of just having a single head that predicts the next token, you introduce n additional heads that predict the n future-looking tokens, so the next token beyond that and the token beyond that, et cetera. And then you have a simple kind of verification step that runs to say, hey, are these tokens correct? Is it what the model would have originally produced? And if you're guessing these tokens right, more often than you're getting them wrong, then there's a good chance that you can get up to a 2 to 3x speed up in throughput as a result of using these speculative decoding strategies. And in practice, I think what people have found is that these fine-tuned speculative decoding strategies far outperform the kind of non-fine-tuned ones, but do require a little bit of work to fine-tune them. And so, that's probably the biggest barrier to their adoption today. But if we can make that more accessible to people, this, I think, should be a no-brainer kind of technique that people apply. Is if I know I'm going to prompt my model with a specific query pattern, I should just be creating these fine-tuned Medusa adapters and getting a 3x latency improvement just every single time. Control vectors are another one that I think is quite interesting, similar to kind of preference optimization, where you say, I want to steer the model in a particular way to have a particular type of output. And the way that you apply it is quite simple and quite elegant, I think, is you just essentially have this control vector that you add to the hidden state of each layer. And then you go ahead and say, okay, now the new hidden state is just the previous hidden state with this control vector added in, and that's essentially all you do beyond what's been done originally. There's a little bit of work to create these control vectors at training time, but unlike normal fine-tuning, there's no stochastic gradient descent. You just use principal component analysis to generate them, and so it can be quite quick. You can generate these control vectors on the order of like 60 seconds or so. And it generally outperforms techniques like few shot quite substantially, which is very interesting. And here's just a quick breakdown of some of the different applications of this that were explored in this paper that was published last October. So you can do things like try to enforce certain honesty principles or emotional principles, fact editing, things like that. So there are lots of different applications that you can use to steer models in different directions with this. And then finally, model merging. I think this one is also very interesting in the context of, what if we didn't have to know which adapter we want to use for any particular prompt? What if we could just kind of combine them all together in some way, either in like a mixture of experts-based system or just merge all the different weights together in some way? And the nice thing about these techniques like ties and Addair that do this model merging is that they operate on these task vectors, they call them, or you can call them like the delta weights between the base model and the fine-tune model. And the nice thing is that things like LoRAs are already these task vectors by their nature. And so you can very easily merge them together using these techniques and get good results. This is actually something we've already added to LoRAX, is you can basically say, all right, merge all these different adapters together using this merged adapters object, apply certain weights to them, use a certain merge strategy like ties. And then when I go ahead and prompt the model with a particular prompt, it should be able to figure out what combination of adapters contributions ultimately constitute the response to the question. And so you can have it have a single kind of logical adapter, if you will, that can serve all these different use cases at the same time without having to explicitly say which one you want to use. So quite an interesting direction. It's still pretty early days, but I think could be very promising in the future as well. And very last thing I'll say is a bit about productionizing this. So at Predibase, we built out kind of a managed version of this platform with the ability to serve multiple different replicas of a system like LoRAX behind a single networking layer, behind the load balancer. And there's also a lot of things you can do to optimize this on the networking side, one of which is how you think about load balancing. So you can imagine load balancing across different adapters based on a policy that tries to pack adapters together on the same physical deployments. And the reason why you would want to do this is to reduce memory overhead, of course, that if you don't have redundant copies of adapters living on different pods, you can reduce your kind of overall aggregate memory overhead, and also improve batching by ensuring that you're always able to batch together requests for the same adapters because you're not trying to load too many on a single pod. And so in theory, you should get much better performance characteristics by doing something like this. And that's about it for this talk. So yeah, just summing up, don't do one dedicated deployment per adapter, do something like LoRAX to pack them all together. And if you are interested in checking out LoRAX, definitely go ahead and give it a star on GitHub. It's fully open source, free use commercially, all of that good stuff. So please check it out and let us know if you have any feedback on it. So thanks, everyone. Go ahead and hand it back to you, Bo, and happy to take any questions if there are any as well.
Thank you, Travis. So this is a very informative talk. Thank you so much. And so any questions from our audience? You can either unmute yourself or input your question in the chat box. So actually, I have several questions. If maybe I can ask first.
Sure.
Okay. Yeah. So first, so I would like to ask. So here your talk, the title is about the LLM. So I was wondering, so whether we can also apply to the other generative model like the diffusion style model.
Definitely.
If so, is there any kind of the specific challenge and or the unique optimization opportunities you can leverage there?
Yeah, definitely. So I do think that a lot of these, particularly multi-LoRa techniques, are applicable to diffusion models. I'm not as familiar with diffusion models because I haven't worked as kind of low level on the optimizations for those as I have with LLMs. But my understanding is that definitely LoRas are very popular in the diffusion model community, and merging different LoRas together is also very popular. And I definitely have seen some projects, like I think the Hugging Face Diffusers project that has started to implement some of these multi-adapter inference systems. So it's definitely something that's taking off over there as well. In fact, I think a lot of the really interesting ideas around parameter efficient serving for LLMs kind of starts in the diffusion model community and then kind of works its way to the LLM community later on. But yeah, definitely like, again, not as deep into that field as I am with LLMs, but I do keep an eye on it because I think a lot of interesting ideas come out of the diffusion model community that then ultimately end up being, some fraction of them end up being applicable to LLMs as well.
Okay, thank you. And actually, I have another follow-up question. So at the end of your talk, actually, you mentioned several different techniques, and among them, so which one do you think is kind of more promising, or
Yeah,
what is kind of pros and cons, especially from the perspective of the practical deployment in the industry?
yeah, definitely. So I think classification is one that is very interesting in terms of its general applicability to a lot of real world problems that people have. Like text classification still continues to be, like, even in the world of LLMs, like one of the most common use cases that people have. I think the one maybe downside to classification as a use case is that I actually think that typically decoder-based models are not the preferred architecture for doing classification. That, like, encoder-based models like BERT tend to be particularly popular and well suited to that. So while I do think this is a very promising one, the classification one, I do think that LLMs in particular are not always the right solution for it. Embeddings is one that I think is interesting because we have seen some promising directions where LLMs can be good embedders as well as generators. And particularly for RAG workflows, there's a good case to be made that you want to kind of jointly optimize the embedder and the generator and even the ranker together. And if you can have one kind of base model that does all three, and then have just adapters that specialize for the embedding generation, the ranking, and then the generation, that could in theory be a really nice kind of combination. So this, I think, could be very promising for RAG applications where you want to have domain-specific adapter for embeddings and then a domain-specific adapter for generation together in one deployment. This is the one I'm probably the most excited about, like, right now, which is speculative decoding, because I do think a lot of people that are trying to solve LLM use cases today, throughput and latency tends to be one of the things that's top of mind right now, is how do I get the best performance, right, for my use case. And speculative decoding, I think, is a very easy win in that case. If you can say, I know that the types of inputs I want to send to the model are constrained in some way so that I'm only going to be prompting it in for certain types of things, then it makes very perfect sense, I think, to generate an adapter like this, because you're almost guaranteed to have significant performance improvements, like 2 to 3x in those situations. And then control vectors, I feel like this one's very early days, so I'm not quite sure all the applicable scenarios for this. I'm not sure how much better it is than prompt engineering, as an example. But that said, I do like the fact that it's very cheap to generate. Like, you don't need a lot of data. It's not expensive, like fine tuning. And so I think it could be an interesting avenue for bridging the gap between someone who only is familiar with prompt engineering and prompting, like OpenAI and things like that, to fine tuning, which tends to be this kind of big barrier for a lot of people, where they're a little bit intimidated by data preparation and how long it takes to train a model, et cetera. So control vectors, I think, could end up being an interesting kind of middle ground where you start with prompting, then you graduate to control vectors, then maybe you graduate to fine tuning after that. So I'm not quite sure yet, but I think that's directionally how I'm thinking about it today. And then model merging, I think this one is still very early days in my opinion, but I think could be very promising, because one of the most exciting things about these sorts of multi-LoRa parameter efficient serving systems, I think, is that if you could imagine creating like a repository of LoRa's that's like, a database of LoRa's that covers like every task imaginable, right? Then in theory, you wouldn't need these massive general purpose LLMs anymore. All you would need is some small base model, and then kind of a routing architecture that figures out what adapter to use for any particular task, any particular prompt that you have, and then you just use the right adapter or set of adapters per prompt, and you get as good a performance as you would with like a much, much larger model. So exploiting kind of that sparse activation concept that MOE models use, but in a way that's even more aggressive than what they do today. So I think this is very early days, but I think I'm very excited about the potential for it.
Thank you, thank you. So I guess, sorry, I have another question just inspired by your last slide that about model merging. So we know that actually there exists some debate in the Silicon Valley. So whether we need kind of the OpenAI style, those the general purpose LLM, or we should have kind of more a series of the kind of smaller but the kind of more kind of domain specific models. So actually because we have kind of the similar kind of the history before in the system society, so we know that. So we have the kind of general purpose CPU, or we have kind of domain specific like accelerators of the GPU and so on. So how do you think that about the kind of the future of such debate from your perspective?
Yeah, I think that's a great question. I personally think that there's a world that I think is most likely where both continue to be popular for different applications. I think that general purpose models like GPT-4, I think will always have a place, particularly for consumers, where the space of different questions that they might ask is very broad. And so I do think that having general purpose models could be very useful for that, maybe augmented with like task specific adapters in some way to make it even better. But I do think general purpose models can be very useful for very open-ended applications, at least in the short term. I think that where specialized models make a lot of sense are on very mission critical, business critical, like high value tasks for organizations. And so as an example here, when I was at Uber, we thought about each of our ML models that we were productionizing in like a tier system, right? It was like tier 1 models are the ones that get queried, thousands or millions of times a day, right? And, drive like core business value, like predicting ETA for your Uber ride, or, the feed recommendation models for Uber Eats, things like that. And then you have kind of more long tail models that are maybe not as mission critical. And, if like it goes down because of an outage or something, like no one's really going to notice. I think that the nice thing about pre-trained models and these general purpose models is they kind of open the door to solving a lot of those long tail problems, whereas those types of problems maybe never used to get a lot of resources or attention, or would never be able to make any progress on it. Now, like one engineer who knows how to prompt OpenAI can make progress on that. But I think once a problem starts to transition from a toy POC to something that's in production and that gets queried every day, and that has a certain service level objective associated with it, where it's like, oh, if it goes down, like that actually costs us thousands of dollars, right? Then you start to care more about what's the latency on this system? What's the throughput? Like, do I actually have any guarantees from the provider, the model provider, that they're going to agree to certain uptime, right? And in those cases, I think having these more specialized models is the natural place to go, because they're going to be cheaper, they're going to be faster, they're going to be more reliable, simply by virtue of being more specialized, right? And so I think that definitely as businesses mature with AI, we're going to see more and more specialized models become popular, just by virtue of like the cost argument, if nothing else.
So do you think that similar to the current system, so we have kind of heterogeneous system, so whether in the future we have kind of heterogeneous kind of AI system, we have kind of centralized one kind of the controller style general purpose model, and then cooperated with several more kind of mass specific model?
I think that that'll be true for some open-ended problems like chat applications. Like I think that chat is a really good example where you can imagine having an orchestrator model that figures out, okay, what task-specific model do I need to use to solve this, to answer this question, right? So those I think are like applications where you can have both. You can have like a general purpose model and task-specific models. But where I think task-specific models will be maybe replace general purpose models is for those applications where it's more like an API, where it's like, hey, get me the ETA for my Uber ride, right? It's like it's a single API call. You don't have to do any kind of human level reasoning in order to determine like what's the right model to use. And your primary constraint at that point is latency, right? It's like how fast can I get that answer back? I think those are cases where these more specialized models will kind of uniquely replace general purpose models in the long term. But yes, certainly for open-ended applications like chat, I think architectures like that will become more popular.
Okay, thank you. And maybe someone else want to ask a question first? Yeah. I think there's one question in the chat box. Can you see that?
Yeah, so the question is, the Medusa technique is impressive. If it works well, it can greatly accelerate the speed. As you mentioned, the speculative decoding strategy may require some additional effort. In what areas do you plan to make improvements in the future? So yeah, I mean, I think Medusa is a very promising technique and has become pretty popular in the industry. I would say the one big challenge with Medusa that exists today is that while it is kind of parameter efficient, it's actually not particularly parameter efficient. So for example, a Medusa adapter on a 7 billion parameter model can be about 800 megabytes to a gigabyte in a lot of cases. And that's because the LM head of the model is actually one of the larger layers, and you have to replicate it like 3 to 5 times for each of the speculative tokens, like however many LM heads you want, or speculative heads you want to add. And so it can add up quite a lot. So actually, this is one area where I think there's been some interesting work recently. Apple actually published a paper recently called Speculative Streaming, where they proposed a technique that promised to have performance improvements similar to Medusa, but with about 1/1000th or 1/10,000th the number of learnable parameters. So a much more parameter efficient technique. Another thing that I've been exploring with some of my colleagues at Predibase is a low rank version of Medusa, where you essentially take the LM head and then you create a low rank decomposition of it, and then learn that and see if that has any negative effects on the performance. And if not, then that should give you a nice multiple order of magnitude improvement on the overhead of the adapter while still giving you the same benefits. So that's, I think, where there's still some room for improvement on techniques like Medusa is on the parameter efficiency aspect of it. And then I won't speak to the throughput optimizations that people will make there because I'm not as much an expert on that.
Okay, so some other questions from the audience? Okay, I promise this is one last question. So as a researcher in the industry, so we know that the resource gap or the imbalance between the academia industry become kind of larger and larger. So do you have any kind of suggestions or the recommendations to the researchers and the students in the academia? So if they want to dive into the exciting area of the generative AI, so what is your suggestion for the
Yeah, I mean, I think that definitely there's a lot of interesting research, in my opinion, that is on efficiency that does not require, having access to DGX boxes or anything like that. Like, I actually think that the most interesting work, in my opinion, is the work that's trying to make LLMs run on commodity hardware or run on small, pretty cheap GPUs. That's, a big focus of a lot of the work that we do at Predibase. So I would say focusing attention on how to bring the costs down. I mean, maybe, yeah, one thing I would definitely say is that I think it's certainly in the interests of companies like NVIDIA to constantly be pushing more and more expensive hardware and things like that. But I think it's actually in the interests of most people to try to think about how to more efficiently utilize the resources that we have available to us and to actually kind of make it more accessible to running on laptops, running on phones, things like that. So I would say my recommendation would be try to focus on solving those types of problems and not necessarily on the high scale, running on a million GPUs type problems. I think that those are certainly, locked away behind having access to certain resources. And ultimately the benefits of that research will be locked away to some extent as well.
Thank you. This is a very valuable suggestions. Okay.
Thanks.
So if the audience don't have no more questions, so let's thank our speaker again. So thank you so much, Travis. So this is a very, very interesting and informative talk. And also look forward to your future exciting work in the down the road. And hopefully we can meet in the person in the future. Okay. And
Absolutely.
okay. So
Yeah. Oh, sorry, go ahead.
okay. Also, thank everyone for attending our this week Rogers Efficient Seminar talk, and see you guys next week. Okay. Thank you, Travis. Thank you.
All right. Thank you, everyone.
Thank you.
Bye-bye.
Have a wonderful day. Bye.